The two weights are suspended by cables with a frictionless pulley at point C. Find the forces in cable AB, BC, CD, and DE. Also find the angle theta DE. Note that cables BC and CD are actually the same cables, just sections on either side of our pulley. I have set up my engineering paper with the given and find information. The first step is to draw the free body diagram. In fact, in this problem, we'll have two free body diagrams. We can draw one at point B and one at point D. Okay, I've got my two free body diagrams, one for point B and one for point D. In each diagram, I have shown all the forces, both known and unknown, and the directions, also known and unknown. Next, I'm going to write my equilibrium equations for point B. We'll have two equations, and we have two unknowns, so we'll be able to solve for both of our unknown forces. Here are my two equilibrium equations. Notice in both equations I have two unknowns, force AB and force BC. That means I can solve them simultaneously. And there's various ways I could do this. I could do a substitution and solve, or I could use a solver on a calculator. The method I used to solve this was Microsoft Excel. I took my two equations and broke it up into a matrix and two vectors. First, I formed this coefficient matrix, which has in it the values of the cosine of 50 and the cosine of 30 in the first row, then the sine of 50 and the sine of 30 in the second row, multiplied by my unknown forces FAB and FBC give me 0, or, moving negative 100 to the other side, a positive 100. Then I can rearrange that equation to solve for FAB and FBC by multiplying the inverse of this coefficients matrix by my constants vector. So here's my inverse matrix. I multiply it by my constants vector to get my answers, 87.94 pounds and 65.27 pounds for force AB and force BC respectively. So I've got two of my 5 unknowns. Now I'm going to move to point D, and I'm going to use the free body diagram for point D to write my equations of equilibrium. Okay, I've got my two equations of equilibrium for point D. It looks like we have 3 unknowns in both equations. That's too many unknowns, but actually there's only 2. Let's go back to our problem. If we look at it, we have a pulley at point C, and it's a single cable that goes from B to C to D. So what do we know about pulleys? Well, the force in the cable on either side of the pulley is going to be the same. So the force in cable CD is equal to the force in cable BC, which we found previously. So now we've got force CD. So that reduces our unknowns to 2, and now we've got 2 equations and 2 unknowns. I'm going to rewrite these equations by substituting in the known values and put them in a little bit easier form for working with. Okay, here's what I've done. I've taken my first equation of equilibrium in the x direction, and I substituted in for FCD, 65.27, then multiplied it by the cosine of 65. That gave me negative 27.584. Then I rewrote the equation to put all of my unknowns on the left side and my known constant on the right. Then for the second equilibrium equation, in the y direction, I substituted in 65.27 for FCD times the sine of 65, then subtracted 75 from that, and that gave me my negative 15.845. And then I rearranged the equation in this form. Now I've got 2 equations with 2 unknowns. I can't use the same technique to solve for my 2 unknowns that I used previously with the matrix because of this unknown angle. It just makes that not possible. So instead I'm going to use another, I won't call it a trick, I'll call it a tool that you should be aware of that is very handy. And this tool is based on this information. The sine is the opposite side of a right triangle over the hypotenuse. The cosine is the adjacent side over the hypotenuse. So the tangent then can be written as the sine over the cosine. I'm going to take equation 2 and I'm going to divide it by equation 1. My FDEs will cancel out and I'll get the sine over the cosine of theta DE, which will then just be the tangent. I'll have one unknown left and I can solve for the angle. Okay, this is what it looks like. I've taken equation 2 divided by equation 1. Notice the FDEs cancel out. Sine over cosine theta DE becomes the tangent of theta DE, and 15.845 divided by 27.584, 0.5744. Solving for theta DE equal to the arctangent of 0.5744, I get 29.87 degrees. Now I'll just substitute the answer for theta DE into either of my equations 1 or 2 to solve for FDE. I'll use equation 1. And now I find my final unknown. And we're done.